Alright everyone, let's go through the gas laws. Specifically what I want to do here is I want to go through the derivation of these gas laws and explain where all these little things come from. If you've been in pre-AP before, you've seen this. If this is your pre-AP class, then this is a good intro lesson for you as well. From the kinetic molecular theory, we're told about the behavior of gases. We're told that for example, gases have a negligible volume. In other words, their size is very small, but they take up a lot of space because gases will always fill up their container. So we know that one important variable when we deal with gas laws is volume. Another important variable when we deal with gas laws is pressure, because the particles in a gas are always exerting a pressure on the walls of their container by making collisions. Then another variable that the kinetic molecular theory tells us about gases is that they have a temperature. That temperature is a reflection of the average kinetic energy that the particles of a gas has in its container. So in other words, how fast they're moving around. And another important thing is simply how many particles there are. The kinetic molecular theory doesn't really spell that out, but that's fairly common sense. How many there are is important. So what each of these gas laws that we see on the left-hand column do is try to explain the behavior of a gas if you look at 2 or 3 of these variables at a time. The first 4 look at 2 variables at a time. Boyle's law looks at the behavior of just P and V together. Now for all of these, if I look at 2 variables at a time, I have to assume that the other 2 are being held constant, and that's very important. So T and N is constant. Constant temperature, constant number of particles, and then I can adjust pressure and see what the volume does. So it's just a PV. Now think about this, just do a little thought experiment. If you have a balloon and you squeeze it, you're making the balloon smaller, so its volume goes down. What happens to the pressure inside of the balloon as you squeeze it? From your own experience, does it go down or up? Well, obviously it goes up. You all know that. So as volume goes down, pressure goes up. If we're going to graph that, as the pressure, well, let's just do it this way. As the volume goes down, the pressure goes up. So we get that kind of relationship. And it doesn't go through 0 because the volume can never be actually 0 for a gas. This is what we call an inverse relationship. Mathematically, it's y is proportional to 1 over x from your algebra class, if you were going to graph that. I know that looks like X, but I meant this to be a Y right here. Now, the last column is formula. Now I'm going to put not parentheses, but quotation marks around formula. It does look like a formula. It is a mathematical expression you could substitute into and solve for, but these are really just proportions. So I'm going to put that here just to keep it simple. If you understand the relationships, you can remember these so-called formulas. They're very simple. So if P and V are inversely proportional, that means that they go right next together because PV equals a constant. And that goes back to this expression I put right here. Y times X will be proportional to 1, or a constant will be more accurate there. So what we do, what you've learned in pre-AP, is P1, V1, saying the conditions of pressure and volume at the beginning, or at initial conditions, is proportional to the pressure and volume product at a different set of conditions. So we say P1, V1 equals P2, V2 is what most people think of when they refer to Boyle's law. All right, that's our first gas law. Let's move to Charles's law. Now, Charles did experiments also looking at the volume of a gas, but instead of pressure, he was more interested in what temperature does to a gas. So keep in mind now, pressure has to be held constant, and then the number of moles has to be held constant for Charles's law to work. So he did his experiments, and let's do our own thought experiment. Let's take some temperature and let's increase it. So let's heat up, say, a tire or a balloon. What's going to happen to the size, the volume of that tire or balloon if I heat it up? Up or down? It's going to be also up. So we have a different type of relationship here with Charles's law. If I graph V versus T, I'm going to get a straight line. And it doesn't go through zero either, because volume doesn't ever equal exactly zero. My graph here wasn't very good. It's really close to the origin. Very, very close to the origin. So that was a terrible graph, but we're going to deal with it for now. But here, Y, I'm going to substitute Y. I didn't really like that. Volume is proportional to temperature. Okay, so that is directly proportional. Or just direct is fine. Now, mathematically, if you can look at this expression we just written here, this will look different than Boyle's law because V and T is direct. And if P1, V1 is next to each other in inverse, then if you're direct, they're going to have to be on top of each other. So we do it this way. This is how we get what is commonly called Charles's law. It does not matter if you put the V's or the T's on top, as long as they're consistent. In other words, a T1's on top, T2 needs to be on top. And as an algebra hint here, if you do, let's say, solve for a variable, it's more difficult if the variable you're solving for is on the bottom, so it's okay to flip the entire equation upside down and put the variable on top. That works perfectly fine. Okay, moving on to Gay-Lussac's law. He looked at pressure and temperature instead of volume. If you've ever popped popcorn, this is what you see with popcorn. As you put it in the microwave, the temperature goes up. So therefore, inside the kernel, the pressure goes up until it pops. So we have another direct relationship. I'm just going to give it a D there. If it's the same relationship, the formula is going to look the same as well. And I just put P on top again because just for consistency's sake with Charles's law, but it works the same. Like I mentioned, flipping the entire thing, if you need to solve for a variable in the bottom, you can just flip it upside down. All right, moving a little more quickly now. Avogadro's law is a little different. He looked at volume, but this time he's looking at the number of moles. So pressure and temperature are constant. You've all done this. If you look at moles as the number of particles, pretend you're breathing into a balloon, you're blowing it up. What happens to the volume of a balloon as you blow into it? It increases, that's right. So it's another direct proportion. So we'll have, again, this type of equation, which is just a proportion. If the volume doubles, what happens to the number of moles, or what had to happen to the number of moles, then it also had to double. That's what we mean by direct. Now the combined gas law is a little different. This time we're not going to look at just two variables. We're actually going to look at three. We're going to look at the pressure, we're going to look at the volume, and we're going to look at the temperature. So the only thing being held constant here is the number of moles. So this would be like a closed balloon or a tire where the air can't get out, something where the number of particles can't change. Well, we've already worked out what the relationships are between P and V, and then we've already worked out what they are between V and T, and also P and T. So we're just going to combine what we already know. The relationship here, and for this particular gas law, this box isn't so easy we know that we have the PV inverse. I'm just going to put an I. We know we have the PT direct, and we know that we have the VT direct. So we're combining all those things, but mathematically, if we just start with the Boyle's law, we have P1 V1 equals P2 V2. You're like, well, where is the temperature? Where's it going to go? We've already worked out, if you look at Charles's law and if you look at Gay-Lussac's law, I already have temperature in those related to P and V, and it's always on the bottom. So if I just combine Charles's law and Gay-Lussac's law with Boyle's law, I get what we call the combined gas law, and I hope you can see why we call it that. Now for the next gas law, it's probably the most important, because the next gas law we're going to look at is ideal. And we talked about before, the ideal just means you do everything the kinetic molecular theory tells you to do. But when you look at the ideal gas law, all four variables are important. So P, V, N, and T. So nothing is held constant. And you can do proportions with the ideal gas law, but what we're going to do first is derive like where the ideal gas law actually comes from. So let's start out with what we know. We know that pressure is proportional to 1 over V, or say it differently, P is inversely proportional to V. We know that V is proportional to T, and we know that P, let's don't do that one, V is proportional to N. So we have Boyle's, Charles, and Avogadro's law here. Now, let's start again with Boyle's law. We know that we have this relationship here, inversely to V. And let's go back to Charles's law. We said that, V and T, if you're checking those, then everything else has to be held constant. So if I rearrange this, I'll get a constant is proportional to, and it's actually equal to, but for the sake of this derivation, it'd be T over V. And then for Avogadro's law, we do the same thing. A constant is proportional to N over V. Now, once we've done that, I see that I have expressions for relationships between V and the other variables. So if I go back to my Boyle's law here, let's combine some expressions for V and T. I see that T is always over V because they're direct, and so is N. So this is very similar to the combined gas law in that I've combined at least 3 of the other gas laws, but this time all 4 variables are involved. Let's rearrange this a little bit, and let's say that P times V is proportional to, I'm just going to write it this way, it just looks a little better, NT. Now that makes some weird kind of looking new variables. I want to make a graph of P times V and N times T. So at this point, some of you are like, what are you doing? This goes a little bit into physics, so I don't want to get too stuck on this, but this PV is a real thing. It is a work term in physics. And NT is also a real thing in physics. It is a measure of energy. So this is a work energy proportion. This is a valid proportion, but we're going to keep it in the variables that we're familiar with. If we graph these, and if it made you feel better, we could just go y proportional to x and kind of have that here. We would still get a straight line. It is a direct proportion here. And it turns out that there's a value associated with this. A value is a constant that we call R. And R has lots of different units, but we call it 0.0821 liter atmospheres over mole K. And of course the value of R can change if you change that pressure unit. There's lots of different values for R, but that's just a typical one. So if we replace this now, PV is no longer proportional to, it is actually equal to NRT if we put our R in. You're like, where does that come from? Well, let's explore this. And think back to algebra. Y has always been proportional to x, but if we graph it and we do rise over run, we know that y is equal to exactly mx, where we have the slope. So this r here isn't real fancy. It's just the slope of the line that we got from graphing PV, the work term, times NT, the energy term. But all that just to say that the ideal gas law formula comes out to be PV, that is PV equals nRT. We call it PIVNRT. Now, you could do a proportion. I'm not going to worry about this box for the ideal gas law because it's all of the previous relationships that we've looked at. But let me just show you this. You can do a proportion, and there are times when it's helpful to do so. If I do P1 V1 equals N1 over T1, you can use the ideal gas law at different conditions like that. And of course, R cancels out. So you can have a PV over a P1 V1 over P2 V2 equals N1 T1 over N2 T2. That does work. All right, the last two gas laws, Daltons and Graham's. Daltons is very important for AP chemistry. If you look back at our first four gas laws, you notice we kind of left out one possible combination. Dalton's law looks at the relationship between P and N. Now, this one's a little different because we've learned that gases create pressure by exerting a force on the walls of their container. So the molecules, the number of molecules is important to creating pressure because it's the number of particles. And that's independent of the gases. So the unique thing about Dalton's law is that it doesn't just apply to a single gas, like for example helium in a balloon, but it applies the same for a mixture of gases, for example air in a balloon. As you increase the number of moles, the pressure goes up, and each gas does it independently in a mixture. So, keeping it real simple, we have another direct proportion here, but we have to keep in mind that it's also for a mixture, so it's independent. We're going to have a separate video on Dalton's law. Just real quickly, the main idea is the total pressure is equal to the sum of the partial pressures of each gas in a mixture. And that's good enough for this video. If you want to see a proportion like we've done before, there is one. We hardly ever use it, but it would be P1 over N1 equals P2 over N2. Very similar to what you've seen already. And I'm going to erase that so I can have room to finish the Graham's law. And our final gas law is Graham's law. Again, we'll have a separate video on this one, but I just wanted to have a page here, have it on the same page as everything else, just so we can have a nice, concise summary page. Graham's law deals with the motion of particles. So the thing that we're dealing with here is actually a different variable. It's effusion. So what we're dealing with is the molar mass and then rate. Rate or time, but just for now, rate. And we've discovered that if you graph this, the main idea is that as gases get heavier, they're going to move slower. And that is an inverse relationship. But it's not just simply inverse, it's square root inverse. So let me try this again. I'm running out of space here. So it's 1 over the square root of rate. Or you can write it vice versa. I'm just going to give you the Graham's law formula here, and we're going to explore this in the next video. So the Graham's law is that rate 1 times the square root of molar mass 1. So it's an inverse proportion, so it should look just like Boyle's Law equals rate 2 square root of molar mass 2. So that's Graham's Law, and we'll look at some work with that and derive some more stuff from it in another video. All right, practice your homework, and if you have any questions, let me know.